Here we have coterminal angles and reference angles. Coterminal angles mean you're going to terminate in the exact same position. So you need to add a full revolution, right? Not just a mirroring quadrant, but exactly in the same location. So you're either adding 360s or subtracting 360s. Reference angle is a little bit trickier. Reference angle is just the acute angle formed with the closest x-axis. So if you have something like sine 200 and they ask you for your reference angle, 200 is out of bounds, it's not acute. So I simply kind of indicate where that is. It's coming down here to some degree, and I need to know exactly its distance to its closest x-axis. I want to wheel all the way back around to here to 360 when this axis is much closer. So that axis being at 180, I know I have a 20-degree deficit. And the other thing I have to always account for is what angle, what quadrant did this first fall out of? Was that positive or negative for sine, right? Landing in that quadrant, is it going to be negative or positive? And so because there's a mismatch, right? Sine is negative here and positive here. 20 is coming out of a positive. This is coming out of negative. I need to account and adjust for that negativity simply because it originated out of a negative quadrant. Another example here. Let's say I got cosine 280. A quick sketch just to realize what quadrant it's falling into. 280 is just past that barrier there. And so this 180 would be too far. There's a closer, more acute exit. And that's going to have a difference of, what is that, 60, 80 degrees. So that is going to be corresponding to cosine 80. Now this is in a positive quadrant for cosine. 80 is in a positive quadrant for cosine. So I don't need to adjust with a negativity in front of that guy. Those are reference angles. Those would be exact same ratios in a calculator. Last example. Let's say I got tangent 500. So the first thing I like to do here is 500. I can't really keep track of those barriers, but it has one revolution. So I'm going to find its coterminal angle first, its identical angle, by subtracting 360 degrees. So subtracting 360 cuts this down to tangent 140. I don't have to worry about matching the sine because these are exactly the same angle landing in the same spot. 140 is too big to be a reference angle, however. So I've got to kind of see where that's going to land. It's just shy of this 180. And now I've got to figure out how shy it is. So that's just a 40-degree deficit. Tangent of 40. Now I got to compare the quadrant it landed in to the quadrant I'm referencing. Tangent, these are negative quadrants. These are positive. 40 came from a positive. My original angle came out of negative, so I need to adjust and write that in my reference angle. It's going to have the same value as negative tangent of 40. Our two special right triangles coming out of geometry helps us build sine, cosine, tangent of those common angles here. So 45, 45, 90, realizing what the ratios of those triangles would naturally be geometrically. My legs are the same, and through the Pythagorean theorem, we learned that a hypotenuse will always have to be a multiple of root 2 in relation to whatever its leg is. Over here on the 30, 60, 90, opposite the smallest angle is going to be your smallest leg, just a plain old x. From there, I like to jump to the hypotenuse, recognizing if I had this doubled, an equilateral triangle, these would have to be congruent. Twice that length would be the same as this. And then from there, that leaves my other odd man out, x root 3, as my opposite 60 ratio length. And then from here, I could build any sine, cosine, or tangent of any of these angles. Sine 30, by simply remembering my SOHCAHTOA. Right? If I was 45, it wouldn't matter what I'm referencing because of the opposite side is x in either case. So I have an x over hypotenuse, which I realized would be 1 over root 2, which we often clean up to root 2 over 2. So I can rebuild my common 45, 30, or 60 sine, cosine, or tangents if I know this geometric ratio. Sine 30 here, similar deal. Through the lens of 30, through the perspective of 30, the opposite side would be x over hypotenuse 2x. Those x's, regardless of the sides of the triangle, would always cancel out and would always be in the ratio of 1 to 2. You do this with sine, cosine, or tangent for any of those degrees. Another useful chart to generate these common ratios for sine and cosine, we have the square root numerator over 2. So this is going to work for 0 through 90, and to generate this chart, you're just cranking out a 0, 1, 2, 3, 4, and then doubling back 0, 1, 2, 3, 4, all over 2. So let's see how to use this chart. If I have something like the sine of 60, I'd go to the sine row, see where it cross-references with a 60 column. I see there's a 3 there, but it's inside this square root. So I know that's root 3. And the denominator is always just a plain 2. So that ratio is given to me there. Cosine of 60. Go to cosine row and 60 column, and that lands on 1. Now the square root of 1 is still 1. So I can just simplify it as 1 over 2. Yeah, cosine of 60 is a half. Yeah, I was right. Further, it gets these kind of quadrantal angles too. The 0 and 90 gets involved. So if I had the sine of 90, see how that would play out. Sine under 90 would be 4, but it's the square root of 4 over 2. And so that simplifies to 1. Yeah, it works out for that guy too. And cosine 90. Cosine 90, the square root of 0 is 0 over 2, simplifies to 0. So even those quadrantal angles work and are incorporated in this graph here. Each trig function has a reciprocal trig function associated with it. Sine has cosecant, and that is simply the ratio of hypotenuse to opposite. Cosine has secant, hypotenuse over adjacent, and tangent goes to cotangent, adjacent over opposite. Now all these and their reciprocal buddies follow the same positive-negative quadrant pattern, right? Sine following the y-coordinate on the unit circle is going to be positive in the first and second, negative in the third and fourth. Cosine tracking the x-coordinate, the x ratio, is going to follow a positivity to the right of the y-axis and negative to the left. And tangent being a combination of both of those, positives makes positive, double negative makes positive, and as a mismatch makes negative as well. So not only do these sine, cosine, tangent follow these patterns, but also the reciprocals following the same pattern. Now one way to link all three of these positive, negative quadrants together, you might see this A, S, T, C. And this is simply telling you where each function is positive. They're all positive in the first quadrant. Only sine is positive in the second quadrant. Only tangent in the third. Only cosine in the fourth. All seniors turn crazy. Helps you remember where every function is positive and negative. One game you like to play with these trig ratios and their reciprocals is find the other 5 trig functions. So they'll give you one trig function with some parameters on the domain and ask you to find the other 5. Now regardless of whatever one they give me first, I always produce the graph, the table in the same format. Sine through cosine and their corresponding reciprocals. And then whatever one they happen to give me, I fill it in where it lies on the table. So negative 5/3 was given, and I'm trying to generate all the other ratios based off that one. So the most natural place to go would be to its reciprocal, right? I have all the pieces, I just need to flip them over. It's not opposite reciprocal, still negative for both cases, but it's certainly flipped. 3 over negative 5. Now understanding that cosine is the ratio of adjacent to hypotenuse, I realize I have one leg and hypotenuse of a right triangle. So if I were to kind of do some Pythagorean work down here, I could find that missing leg. I see 3, 4, 5 emerging. I know x is going to be equal to 4. The math can prove it as well. So I could jump up here to sine and say that's going to be 4, the other leg, over the same hypotenuse. Its reciprocal would be flipped over, of course. Down here with tangent, that's just a combination of sine over cosine, or opposite over adjacent leg. So 4 over 3 for him. And cotangent would be the reciprocal, which would be 3 over 4 here. Now I also got to account for who was positive and negative. So secant was negative. I know that only happens for him in these quadrants to the left of the axis, and it gave me a parameter of 0 to 180. So it said somewhere within this range that was also negative. I know everything must be based out of that second quadrant, based off the range and the sign of the trig function they gave me. So now I just simply need to match sine in relation to that second quadrant. Sine is positive there, so these can stay positive ratios. Tangent is negative there, so I know their ratios must be made negative for those cases. So I got to kind of double check, scan over, see which quadrant these are coming out of, make sure a variable has the right positivity.